Hi, in EDC discussions, electronic devices and circuits discussion, we start with the formation of a PN junction and how that is, etc., etc., and then we switch on to diode, isn't it? The function of a diode, the very first beginning, basic component which we discuss in EDC, all right? And that topic which cannot be put aside, diode, current through the diode, and we have an equation for that, how that is derived. Different authors suggest different approaches. One of the easiest approach. All right. So before beginning the discussion, there is a question. What is diffusion? Like one charge carrier is moving from one point to another point. So diffusion. And current defined as a flow of rate of flow of charge, like charge carriers from one place to another place. So when we say this diffusion, if there is existing a diffusion of charge carrier, there existing a current. All right. So this is, I am writing it down. We'll have to look back to it. Diffusion. If I say it's diffusion, it's linked up with the current. All right. We'll have to get back to that one. Diffusion. Wherever we come across that term diffusion, we can link it up to the current, and current we can get back to the diffusion. All right. So considering a PN junction, diode, intrinsic semiconductor, starting from the very beginning, intrinsic semiconductor with equal number of electrons and holes, adding a acceptor atom, trivalent atom, trivalent, that will give rise to P region, isn't it? P type material. And pentavalent on the other half, that gives rise to N type, isn't it? N type. And then we have a junction over here. We have a junction, and be very careful. Now what is P type? The question, what is P type material? What is N type? What is N type? P type material, majority charge carriers are holes. Right? P type material, majority charge carriers are holes. The next question is, don't we have holes on the other side? We have. All right. So important point to be noted. Like P type material, majority charge carriers are holes. And the next question is, don't we have holes on the N type region? We have. So number of holes in the P region and number of holes in the N region. We have a relationship given by Boltzmann relationship. From the beginning, it has come from the kinetic theory of gases, etc., etc. And guys, where the student gets confused here, P region, and because of that recombination and all, we have a P region with a negative immobile charge carrier over this side, that potential barrier, depletion layer. This is the point where generally a student gets confused, overlook. Like N type, we have a positive immobile. That's another case, the formation of depletion layer. All right, even that takes time. The focus is on deriving the expression for the current through the diode. All right, so this is the confusion over here. And if this is the case, number of holes in the P region and number of holes in the N region, we have a relationship given by Boltzmann constant. Boltzmann relationship, which is given as, if I say it's a P, number of holes, okay, it's like a P, talking about holes in the P region, number of holes in the P region, and on the other half, number of holes in the N region. So whatever statement we are making for holes, the same can be applicable for electrons. All right. So which is equal to, number of holes in the P region, number of holes in the N region, e raised to V, let's say V0 by Vt. And now we have to have a clarity of what is that V0 and Vt. V0, barrier voltage, this one. V0 specifically, why? Because it's open circuit. We haven't biased that one. All right. So V0 under open circuit, the diode under open circuit. The barrier voltage, VB, some textbook says it's VB, which is equal to V0. Why V0? Saying that it's under open circuit. All right. Now this VT has VT. VT is equal to KT upon Q. So guys, plugging in, it's a constant, all right. It's a constant, Boltzmann constant. 1.38 into 10 raised to minus 23, something like that. This is 1.6 into 10 raised to minus 19, etc. And this T which is equal to 300 at absolute room temperature, like that. All right. So at room temperature, VT value will be, that could be proved, 26 millivolts. Yeah. unless and until specified for a particular temperature. It's we consider for the room temperature, and VT is equal to 26 millivolts. It can be proved. Go check it. We have no much time for that one. All right. So this is the case. Number of holes in the P region and number of electrons in the N region. This is the relationship. All right. Now, after this diode is for, let me erase this one. All right. So VT at absolute room temperature, at room temperature is 26 millivolts. Remember, you will have numericals based on that one. All right. It won't be like at room temperature. They won't specify, consider VT to be 26 millivolts. No, at room temperature they say, so 26 millivolts. Now, what if this diode is forward biased? In the sense, now P type, so we have anode over here, and the N type we have cathode. This is cathode. So positive to anode and negative to cathode, right? So this is forward biasing. Now, what happens to the, what will be the next consequence? Soon after a voltage, V external voltage, forward voltage is given, VF. So what happens next? Yeah, we have a positive potential over here, positive potential, and now holes from this side, and we have negative potential over here. Focus, I'm rushing. Please try to focus on each and every point. Why? Because whatever is happening over here, the same to be, we have to, that phenomena that has to be reflected in the equation, right? So with this one, what happens is we have a positive potential over here, and the holes, hole gets the repulsion force for the time being, because I'm talking about the hole, isn't it? Now, it acquires a large amount of energy, drift velocity, etc., etc., and it starts hitting this. And in the sense, the width of the depletion layer will be decreasing. If this is the case, we have V naught, and if this is decreasing, in the sense V naught is decreasing, that has to be reflected over here. Right, with the forward bias, or else go back to standard textbooks. They have given very clearly, with the increase in the forward voltage, there will be a decrease in the width of the depletion layer. In the sense, there is a decrease in the voltage V naught, that has to be reflected over here. And once the barrier is becoming thinner and thinner, holes from this side, they start diffusing, and electrons from this side, they start diffusing from N type to P type, N region to P region, because there exists, as we go on increase this one, the width of the depletion layer will be becoming thinner and thinner, and at a point no more barrier, and then all of a sudden the charge carriers will be flowing on either side, from holes from this side, P region to N region, and electrons from N region to P region. And I'm talking about holes, so holes, right? So what happens now? So initially this is the one, with the application of the forward voltage, there will be a decrease in the width of the depletion layer, there will be a decreasing in the barrier voltage, and there will be an increase in the number of holes which are diffusing from P region to N region. See, one factor is decreasing and another factor is increasing. What factor is decreasing? The barrier potential. With the decrease in the width of the depletion layer, there is a decrease in the barrier potential. Alright, so that is one point. And with the decrease in the width of the depletion layer, charge carriers will be crossing, it has no more barrier, right? So charge carriers will be increasing. In that sense, number of holes diffusing from, there is an increase in the number of holes in the N region. There is an increase in the holes in the N region because of diffusion, and that constitutes a current. So how that's once again, number of holes in the P region after a forward voltage is applied. All right, now this is remember this product now, charge concentration into E raised to some constant. Why? Because this is a voltage, voltage, that's now that will be a constant value. All right, remember this product is equal to number of holes in the N region, there will be an increase Pn plus del Pn, increased number of holes in the N region. All right, so this one, and we have barrier voltage over here, V naught, that is reduced, isn't it? By what factor? By Vf minus, in the sense that has to reflect over here. So V naught minus Vf forward voltage upon Vt. Now this difference it's decreasing, right? With the increase in this one, though, there's a difference, like that will be decreasing. All right, now this product, even this product is constant. Let it be equation 1, All right, let it be equation 2. Initially it's number of holes in the p-n region, that's constant, and barrier voltage, that's constant, and Vt at room temperature, that's constant. All right, now even this is constant, even with this discussion, forward voltage is given and charge carriers are moving on either side, even this is constant. Why? Because this factor is increasing and this factor is decreasing. So they track each other and the product will be remaining constant, and so we can say that equation 1 equal to equation 2. Alright, so if that is the case, what we have is a p suffix n e raised to v naught upon vt will be equal to pn plus second equation, which is equal to equation 1 equal to equation 2 del pn into e raised to v naught upon vt into e raised to minus vf for voltage by Vt. Alright, something gets cancelled over here in this expression, guys. E raised to V naught upon Vt, this gets cancelled. Alright, this gets cancelled, and this, it's a product. There was a question, how can that be cancelled with this one? No, it's a one product, it's a one term into this, this into this, so in that way it gets cancelled. Right, so these two on either side, we don't have this anymore, that gets cancelled. And what else can be done? So guys, focus. All right, so it's a negative. If we drag this to LHS, it will be positive. All right, so it will be Pn into e raised to Vf upon Vt. All right, which is equal to that same Pn plus del Pn. And what do we have for del Pn? If that is the case, dragging everything for del Pn individually, del Pn, that will be this Pn, it will be as it is. All right, so del Pn, what do we have? Del Pn will be equal, this will be as it is, and this comes this side, isn't it? P suffix n e raised to Vf by Vt minus P suffix n. So and there something can be taken out as common. All right, so P of n can be taken out as common, so e raised to Vf by Vt minus 1 will be the term del Pn. Guys, now del Pn, it started from here, del Pn, I repeat, focus on this one, del Pn, it started from here after forward voltage is given, and that came into picture because of diffusion, and diffusion is nothing but current, and so this entire equation can be current, it will be current, and it's a this, all the discussion is for holes, so it will be hole current IP. All right, so this is with the hole. The same thing will happen with the electron also. All right, so in that case, what will be del Pn? It will be del, it's for hole in the n region, so what will be del Np, electron in the p region? That will be the same thing, del Pn, isn't it? So Np into bracket open e raised to Vf upon Vt minus 1. All right, so that is for del, this is for the hole and this is for the electron. That's the advantage in this derivation. So whatever we speak about hole, the same thing will happen with the electron. All right, and from the first equation, coming back to the equation, if this is the case for the hole, how can we write the expression for the electron? The same thing, what do we have? P suffix p, hole in the p region. In the same way, electron in the n region, that will be reverse. All right, n suffix p into e raised to v naught upon Vt. All right, the same thing, like this was for a hole and that's for electron. All right, so in this case, what will be Pn? It will be P suffix p into e raised to, it's positive in the RHS, when we drag this to LHS it will be negative V naught upon Vt. Right, so yeah, that is for Pn. And remember, once again, I'm sorry, take a pause over here, come back to this expression. Take a pause over here, come back to this expression. Del Pn took this form. All right, del Pn took this form. What is this form? It's a product. It's a product. Charge concentration into e raised to some value minus 1. This product is a current. Once again we will come across the similar product, even that has to be rounded for a current. Alright, so del Pn, it's a diffusion of hole, and diffusion of hole constitutes a current, diffusion current, hole current, and so this is one. Alright, this product, charge concentration, number of holes in the n region into e raised to something minus, here we have minus 1, in the other time we may have minus 0, like that. Alright, so this product, I'll get back to you. I wanted you to focus on this one. Alright, so if this is the one, this is for Pn. And what will be for Np? Np, also it will be n suffix n, alright, e raised to negative V0 upon Vt. Alright, that's it. Now, even this is for like similar to del Pn, it's a whole current. This del Np will be In, electron current. Whatever happens over this side, the same thing happens over that side. And in a diode, the current will be due to holes and electrons. Alright, not individually holes or not individually electrons. The current in a diode will be like holes from the p region, they start diffusing to n region, and in the same way electrons from that side will be diffusing to this side once the barrier potential is decreasing. Once the width of the depletion layer becomes 0, then it starts, the current will start flowing from that side to this side, and the current is due to both the holes and electrons. So what we have is total current I equal to Ip, current due to hole, plus current due to electron in a diode. Alright, so plugging in these values. So, so Ip is this one, Pn into exponential Vf by Vt minus 1 plus this one, it will be Np into exponential Vf by Vt minus 1. Alright, so some term can be taken out as common from both the terms, this one and this one. So what do we have? Total current I equal to the combination of hole current and electron current, which is equal to Pn plus Np into exponential Vf by Vt minus 1 as common from both the terms. Alright, now even this is a current, but it has another form. Even this is a current. The same Pn, see this, the same Pn, P suffix n, the same n suffix p, the same n suffix p. Check that one. Alright, so what we have is this takes another form, this one. So total current I will be equal to P suffix p exponential rise to negative V0 upon Vt, alright, plus what? This one, right? N suffix n exponential negative V0 upon Vt for this one, Npn, right? So bracket close, and exponential rise to Vf by Vt minus 1. Did I confuse you? No. Pn is plugged in with this one from the very first expression. Alright, so Pn as it is, P suffix p e raised to minus V0 upon Vt plus, and Np from here, Np n suffix n e raised to negative. Alright, so something else can be taken out as common from here. So it's a hole concentration in p region and plus electron concentration in n region multiplied with this can be taken out as common, e raised to minus V0 upon Vt as common into e raised to Vf by Vt minus 1 from the previous expression. So guys, can you see this? It's a product which I asked you to focus this. I've erased that one, we came back to that one. Number of charge carriers into exponential rise to this thing minus 0. Now this can be rounded for a current again. The same product I've said something. IP, the same product. Number of holes in the, it's a number of charge carriers. Alright, so this current is nothing but, guys, This is from the beginning, like majority charge carriers I was talking about, and this is the current. It's a current which is due to minority charge current due to minority charge carriers, and so the notation I naught, and this comes as it is, right? E raised to Vf upon Vt minus 1. All right. So during this discussion, I didn't say nothing came into existence. The discussion about recombination and regeneration. Why? Because with the increase in the temperature, there will be a slight increase in the temperature, and a new electron hole pair will be generated. Right? Even in a small increase in the room temperature, a new electron hole pair generated in the semiconductor devices. All right, so that was not included over here in the sense recombination and etc. So this final expression takes another form: I naught, current due to reverse saturation current, and exponential rise to Vf upon, guys, this should be included, neta Vt minus 1. All right, representing the generation and recombination of charge carriers after there is an increase in the temperature. All right, and it has got another like neta equal to 1 for germanium, and neta the same value, it has 2 for silicon. All right, this has to be kept in mind, and this is the final expression for current through a diode. Thanks for watching.